All right, you guys, I think this is good. Let's see. Why is this so dim? This is really dim on my screen, which was not my intent. Um, Kind of weird. Don't know what that's about. Gosh, it's really, really dim. Okay. I don't want it to be like that. Okay. All right. It suddenly seems better. Okay. All right. So good. Okay, you guys. So here I should have this on the screen here. I hope you can see the same thing I can. Alrighty. I'm making this bigger for me. I don't know if it makes a difference for you at all. Okay. All right, there we are. Riemann sums. And I mispronounced that. Technically, I think it's more like Riemann or something like that, but I say Riemann. And I don't seem to be able to break the habit. So we're gonna go with it. Riemann sums. And so here, basically what the idea is that we in earlier chapters, we found the derivative. We found the slope of something at a given point, the derivative. Now we're going backwards. And so the opposite of taking a derivative is called the antiderivative. And that essentially represents the area under this curve. And so there's lots of ways of estimating the area under a curve. And frankly, we should probably spend like a week just having you estimate areas with a curve, and you get really good at it. And you would find there's all kinds of ways of breaking this shape down. It's just the one that everybody seems to have basically landed on is to use what's called the Riemann sum, which is basically just a series of vertically oriented rectangles. So you just basically break this thing down into a certain number of rectangles, which we'll do in this lesson. And then you estimate the area of each one. And adding those up gives you the total area. Okay. If you're interested in the meantime, and you want to just calculate things, you can see that each of these has an area of 1 square unit. So you could just literally count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on, and come up with a pretty good estimate of this area without having to do all of this background work for Riemann sums. But unfortunately, or fortunately, as the case may be, that's what everybody's landed on. And so you need to be familiar with the terminology and so on. So I'm just going to go through an example. When you do Riemann sums, the rectangles don't all have to be the same width. They can be whatever width you would like. And so this is an example. Imagine that I have a piece of licorice or a red vine that's been placed along the x-axis, and I cut it in the following places. Okay, so if I cut it 1, 2, 3, 4 places, I would end up with 1, 2, 3, 4, 5 subintervals. And so these questions are just going to kind of walk us through that and introduce the notation. So how many little pieces of licorice are there in the figure above? Well, there's 1, and then 2, and 3, a little one there, 4, and 5. And it's totally arbitrary where you make these divisions. It doesn't matter. There's no rhyme or reason to these numbers. You get to pick however you like. So how many little pieces of licorice are there? There are 5 little pieces of licorice. Okay, if we think of the licorice as representing an interval from A to B, we could write it as the closed interval from 3 to 35. Okay, just a word about that. If you were graphing this on the number line, you would probably do something like this: 3 there, 35 there. It takes more ink to fill this in here than to fill these in, just as it takes more effort to draw these brackets. Okay, if you were doing something like this from 3 to 35, you would write it like this, which I know if no one told you, you'd think, well, that's just the coordinates of a point on a graph. But when it's in reference to an integral, this means open integral, and literally O for open. There's very little ink there. And then closed, you'll notice the word closed takes more ink to write than the word open. Okay, and closed, it takes more ink to do this, and closed intervals, it takes more work to draw that bracket than it does to just draw the parentheses. So I didn't mean to make a double parenthesis there. Okay, there we are. So anyhow, this is what the interval would be from 3 to 35. Okay, so the location of the first cut on the interval is denoted as x sub 1. So this is the first cut. That is x sub 1. And the next cut is x sub 2 and x sub 3 and x sub 4 and x subscript 5. Sub means, oh, I'm sorry, wait a minute, that's not a cut. It's going to have me fill that in later, but there we are. Okay, so label these on the diagram above. I got that. Okay, in the future, when we're writing formulas for Riemann sums, it's inconvenient to have to change the formula for the endpoints A and B. And so what we'd like to do is just extend this same exact notation. Instead of calling this A, we could just call that x sub 0 or x sub naught. And then this would be, as I wrote earlier and then erased it immediately, this would be x sub 5. The end of the fifth interval would be x sub 5. Okay, the highest subscript is called n. What is the value then for this interval? Well, the highest subscript here is 5, so n equals 5, which is really handy because that is the exact same thing as this. There are 1, 2, 3, 4, 5 subintervals, and so it is the same. And that's important, and that's helpful and handy that it works out that way. Okay, the numbers on the piece of licorice representing the endpoints and the cuts are known as the partition P. So this is just a set of numbers. So I use the fancy curly brackets. I'm not very good at drawing those. And so we just write down the numbers. It started off at 3. The first cut is at 8. The next cut is at 16, and then 18, and then 29. And the last one is 35. And that is called a partition. And it just means we're just chopping this thing up. Okay, each little piece of licorice is referred to as a subinterval. How many subintervals does this interval have? Well, we've already been through that. It's 5 once again. Okay, the leftmost piece of licorice, the first subinterval, so this from 3 to 8, is represented as a closed interval, and its width is represented as delta x sub 1. So the subinterval, the first one is from 3 to 8, so we write it like this, and the width of it is just how far apart these two numbers are on the number line, and you just subtract 8 minus 3 and you get 5. Okay, the second subinterval goes from 8 to 16, and its width would be delta x sub 2, which would be 16 minus 8, or 8. Okay, and there's no reason to get concerned that 8 is included in the first subinterval and the second subinterval. That is not something to really worry about. Okay, the next subinterval goes from 16 to 18. And so delta x sub 3 is equal to 2. And then the fourth subinterval goes from 18 to 29. So the fourth subinterval, what is that, 11? Okay, and then finally, the last subinterval is from x sub 4 to x sub 5. So 29 to 35. And that is the fifth subinterval's width. And that is what, 6. Okay. And if I add these all up, let me just double check that. This adds up to 10, and then add this 21 and 11 more, 32. And that makes sense because if you go 35 minus 3, you get 32 also. So I've calculated these correctly. I do make mistakes in the videos, you guys. If you find a mistake, I often catch it, but just let me know, email me when you find mistakes. One time I like to get emailed is when there's a mistake in the video, if students email me that. Okay, the widest subinterval is called the norm of the partition, okay? To represent the norm of a partition, we write it, it looks like double absolute value bars, but please don't say double absolute value bars, it's just the norm. So that just means the width of the widest subinterval. So we just find the maximum of these values, and in this case, it would be 11. So the widest subinterval is 11 units. Okay, and then finally, if a partition has 2 or more subintervals that are all tied as being widest, you can still calculate the norm. And so in this case, how wide is this? Well, this one is 7, and this is also 7, and this right here is 7 as well. Is that right? That doesn't seem right. This is not 7. This is 3. I'm adding them instead of subtracting them. This is 3, and that's 7, and that's 7, and this is 1. And so we have these two here. They're tied as being the widest, and so the norm of this, the norm is equal to 7. Okay, this doesn't mean the absolute, this symbol here does not mean that the absolute value of the absolute value. It doesn't mean that. It just means the widest of them all. Okay, all right, guys, we're gonna move on to the next page. Okay, so I need to stop recording, and there used to be a to do that, and okay, it's to stay in the call. Okay, I'm gonna leave the call, and I'll see you at the next video. Okay, bye-bye.